Today's lesson focuses on predicting precipitates. And in order to do this, we will revisit the reaction quotient and compare it to the KSP value. Last year, we used a solubility chart in order to predict whether a precipitate would form when certain ions were in a combination together and had the ability to form a solid compound. So the solubility table is a great thing, but it only tells you whether the combination of ions have a solubility greater than 0.1 molar. And if that happens, then you'll form a precipitate. And sometimes we have concentrations of ions that are lower than that. And so a precipitate might not actually form. And this is of interest to us because sometimes there are toxic ions in some of these solutions that we don't want to have freely floating in water or in our water systems. We want those toxic ions to actually become a precipitate and be sort of like locked in, unable to cause harm to wildlife, humans, and such. So we want to know whether we have ion concentrations that are either high enough to create a precipitate or low enough that they don't create a precipitate. And the KSP value will tell us this. So we always have to compare to the KSP. Here's an example. If we looked at the KSP for calcium carbonate, we know that it's a 1-to-1 ratio of ions here based on the formula, and that together the product, okay, so the multiplication of those two ions has to equal 5.0 times 10 to the negative 9 in order for a precipitate to form. So what we do is we use instantaneous concentrations. We put them into a KSP-like expression, and then we compare them to the K value to see whether we will have the concentrations high enough to form a precipitate. Keep in mind that the concentrations of these two ions don't necessarily have to be equal. Okay, it's when you multiply the two concentration values together, they have to either equal the K value or be greater in order to form a precipitate. So we use the reaction quotient as we've seen in the past. And again, we'll be given instantaneous concentrations, or we might have to calculate the concentration of those ions in a particular solution. And then we compare them to the K value. So we now are going to we still call it reaction quotient, but we'll call it a bit more specifically the trial KSP, which is our Q value. If it's greater than our KSP value, a precipitate is going to form. If it's equal, then the precipitate will not form. We are here, this is just the threshold where we have just reached the point of a saturated solution, okay? Where like if we added any more ion, one little ion, we would form a precipitate, okay? So when they're equal, we assume that we are just at that point just before precipitation would occur. And then if your K value if your Q value is less than your K value, then a precipitate will not form, right? It means that together those ions are too low in concentration. They're not gonna be able to find each other and form a solid precipitate. So let's do an example where we are given concentrations of ions and we're gonna see whether a precipitate would form. So they mix solutions of calcium ion and carbonate ion, and we have the concentrations of each of them given right here. We know the KSP value. We're giving it to you in this question. You can always go to the chart and look it up yourself. And it says, will a precipitate form? So we know that for calcium carbonate, we would have ions forming that are calcium ion and carbonate ion. Now notice I do not use the reversible arrows because we don't know whether we're in equilibrium system. We would be if we form a precipitate, but we just don't know. This is what we're trying to figure out. So we set up our Q expression and we equate that to the two ions. So this is a 1-to-1 ratio of ions, and we would have concentration of calcium ions times the concentration of the carbonate ions. If the ratio of ions was anything other than 1-to-1, we'd be raising them to whatever power, just like we would in a K expression. So we sub in our values. So calcium is 2.3 times 10 to the negative 4 molar, and carbonate is 8.8 times 10 to the negative 2 molar. So again, notice they're not the exact same concentration, and that's okay. Oftentimes, these ions are coming from two different solutions, right? Perhaps in a double displacement reaction, and then these ions are coming together and possibly forming a precipitate. We multiply this together, and we get a value of 2.0 times 10 to the negative 5. Now, we compare this to our K value, and be very careful here. These are negative values. 2.0 times 10 to the negative 5 for the Q value is actually greater than the KSP value. So some students get tricked because they see, a 9. 9 is bigger than a 5. Well, no, it's negative 9. Okay, so this is a very, very small value. And the K value is actually, or the Q value is actually bigger. So when our Q value is larger than the KSP, that means the ion concentration is high enough that a precipitate will form. Let's do another example where we'll have to do a little extra work in order to come up with the instantaneous concentrations. So here they're telling us that they're going to mix 50 mils of 0.0035 molar calcium nitrate solution with 150 mils of 2.0 times 10 to the negative 5 molar sodium carbonate solution. So this is a typical double displacement reaction, and it's asking, will a precipitate of calcium carbonate form? So we're only interested in those two ions, okay, the calcium ion and the carbonate ion. So in the previous example, we gave you those concentrations, and we just said, here are the concentrations, decide whether a precipitate's going to form or not. And we did that through a calculation. Now we're going to have to do a little bit of extra work just to get to that point. So we need to figure out what are the concentrations of each of those ions when they've been mixed together. So the first thing that we do is determine the concentration before we mix. Okay, and the reason we have to do that is in case these ratios of ions is not 1-to-1. So we're going to take some calcium nitrate, and this is a solution that we assume dissolves well in water. And we know that we're going to get calcium ion out of that, and twice the nitrate ion will be released. And we assume all of this is aqueous. We know this concentration is 0.0035 molar. And we are interested in knowing the concentration of calcium ion because that is what is possibly going to form the precipitate. So we notice that this is a 1-to-1 ratio of ions. So this tells me that the calcium ion concentration is exactly the same. We do the same for sodium carbonate. So we have a solution of sodium carbonate. This means that it's already dissolved, it's already aqueous, and we know that we would have twice the sodium ions in solution than we would carbonate. And again, everything is aqueous. I didn't write aqueous over here, but I should. Okay, everything is dissolved and in solution. And the only possible precipitate is, whether these concentrations are high enough. So this concentration of this solution is 2.0 times 10 to the negative 5 molar. And I am interested in the carbonate ion. So when we balance this, again, this is a 1-to-1 ratio, which means that this carbonate ion concentration will be exactly the same, 2.0 times 10 to the negative 5. You have to do this step in case it's not a 1-to-1 ratio. So for example, if I was trying to figure out sodium ions, that's a 1-to-2 ratio. So my concentration of sodium ions would be twice the amount. So you have to check this out initially and calculate the concentration before you actually mix. This is a crucial step. So now that we know the concentration of our ions before we mix them, we now have to figure out the concentration after we mix them. And after we mix them, we are combining two volumes, so we are diluting. We have to recall our dilution formula, which is M1V1 equals M2V2. So we'll just sort of split the page here, and let's first come up with the final, so the M2 is what we're after, final concentration of calcium ion. So we're going to do M1 V1 over V2. We just came up with that initial concentration. Again, we had to account for the fact that the ratio of ions was either 1-to-1 or not, and it was. So we know that the initial concentration of calcium is 0.0035 molar. And when we reread the question, we added 50 mils of it initially. And then we combined that with 150 mils of the sodium carbonate. So my V2 is a total of 200 mils, okay? 50 mils initially of one solution, 150 of the other. When we go through and we calculate the new concentration, we get 0.000875 molar. We have to do the same for carbonate. So we want to know the M2 of the carbonate ion, and we calculate M1 V1 over V2. So again, we went through the work on the previous slide of coming up with the initial concentration of carbonate. It worked out to be exactly the same as the solution because it was a 1-to-1 ratio of ions, but sometimes it's not. And then we took 150 mils of that solution initially, added it to the 50 mils of calcium nitrate, and so we have a total volume of 200 mils. We do the math and we get a new concentration here. It's pretty low, 0.000415 molar. And now we set up our Q expression, and we're going to compare that to the KSP. So again, we're after calcium carbonate, okay, is what we're after here. We're trying to figure out, is this a precipitate that's going to form? It's a 1-to-1 ratio of ions. So we're going to set up a Q expression of calcium times the carbonate ion. Nothing is squared, okay, because the ratio of ions is 1-to-1. We sub in these values that we've calculated. So in that previous example, example 1, we gave you these concentrations, right? It was kind of nice because you just stuck it into the Q expression. Now we made you work for it. And we get a Q value of 1.3 times 10 to the negative 8, okay, which is pretty small, but it is not small enough compared to the K value, okay? So the Q value is still greater than that KSP value of 5.0 times 10 to the negative 9. And so as a result, a precipitate is still going to form. Oftentimes it will. You have to have extremely low concentrations of ions to not have a precipitate form. So there you go, a little bit of review of dilutions and figuring out, again, reaction quotient to determine whether a precipitate will form.